tent. It's very hot in here, so we don't have a lot of people sitting here, but the next speaker is willing to get through that last talk. He's presenting graphs with physics, and I'm really looking forward to it because I have no fucking idea what's coming up now. So please, a warm welcome for Alphotic.
Hello, thank you for coming. So I will be talking about visualization of networks or graphs using physics. It's a topic that will be a combination of computer science, physics, and visualization. This is a brief outline. I will start with an introduction, state what is the problem and why we want to look at it. Then we'll describe how we can draw inspiration from some physical system, physical phenomena to tackle it. Then I will briefly mention some performance considerations in these techniques, and I will present some visualizations. So networks, in the most general sense, represent connections between entities. Those entities can be people, related by friendship or by professional relationship, or computer networks, as many of you probably are familiar with, or transportation networks, connecting stations in a city, or even biological networks, where the things connected could be proteins or genes with some kind of similarity. Myself, I forgot to introduce myself. I have a degree in computer science, and I did my PhD in physics. Right now, I work as a Marie Curie Fellow in the Alexander Fleming Research Institute in Athens, mostly using these tools to study biological networks. In the language of computer science and mathematics, any kind of network can be represented by an object called the graph, which is completely determined by two sets. One is the set of vertices, or the things that are connected to each other, and the other set is a set of the connections, or edges. Just for clarification, I will be talking about undirected and unweighted graphs from now on. As a very trivial example, this is one simple network or graph. There is 3 nodes, labeled 1, 2, 3, and 3 edges, the 3 lines connecting them, from 1 to 2, from 2 to 3, and from 3 to 1. Usually, the graphs are most easily represented as a set of points connected by lines in 2D. And here is the representation for this case, where I have chosen the positions of these points randomly. In this case, it doesn't really matter, because any way I choose them, it will be a triangle, maybe a less symmetric one. But this is just a very simple case. If we want to go to a graph with 4 vertices and 6 edges, it would look, again, random positioning. It would look something like that. Here's a graph with 5 vertices. Here's a graph with 10 vertices. So you see, as the network or graph gets bigger, things become more complicated. It's kind of harder to distinguish what is connected to what and what is the structure there. Here are 2 layouts of 2 different graphs. They have roughly the same amount of points. In one case, 124, and in the other 123. Different number of edges. But here's a random layout of each one of them, and it's very messy, and it's almost impossible to understand what is the structure of these networks. How do they look like? If we choose, though, the positions, the placements of these vertices in a more intelligent way, perhaps, we can see that the graph on the right looks something like this. So it has a very clear structure where there is few nodes in the center that are highly connected, and as you go out, nodes become less and less connected. And the graph on the right, on the left, I'm sorry, looks something like this, where again it's a very simple structure, but completely different from the one on the right. In this case, there is no special nodes that are highly connected. Every node is completely equivalent to another one. So that is the point of being able to do good layout, is first of all to understand the structure that exists in a graph, and also to be able to compare different graphs between them. These two looked almost identical when in the random layout, but very different when choosing a nice layout. So the point of this talk is how can we make these layouts happen, these visualizations happen. In general, the criteria of what is a good layout are not strictly defined, but it's considered, let's say, generally considered good to have a minimum number of edge crossings, so lines crossing each other should be low. The vertices or nodes should be distributed in space evenly, and any kind of structure or symmetry in the graph should be visible. And this is a problem that has been studied in the past, even from the late 70s, initially in the context of laying out the components of VLSI circuits. So the nodes in this case were components in the VLSI circuit, and the connections between them were the edges. And they were trying to find an optimum layout for these circuits. And later on, it was refined, and a lot of the techniques I will be talking about using physical models of physics to visualize graphs is based on the work of these people here. So now we go to another chapter, which is to look a little bit at what happens in nature, in some physical systems. It's often the case that we see structures in nature of high symmetry and high elegance, but at the same time high complexity. Just like, for example, in snowflakes, where we can see the simplicity as well as the complexity in them. So things like that appear not only in this case, but, for example, in bubbles. You might have seen it in a soap or a bottle of beer or a bottle of milk. This kind of 3D structures that form spontaneously, naturally, and create this aesthetically pleasing and symmetric result in many cases. And similarly in the structure of molecules in 3D space. The arrangement of the atoms is not random. It gives a very cool and easy to understand picture of how things are connected. So these patterns appear in many cases, as I said, and in many scales as well, like the molecules and the snowflakes and the bottle of beer have very different scales. And the reason is that there is a common underlying principle governing this behavior, which is generally that any physical system tends to find a point of minimum potential energy. So we can define the potential energy of a system, a physical system, and the forces acting on the system will always push it to a state of equilibrium that is in the minimum of this potential energy. So in analogy to a ball that is rolling down a hill, the ball will always try to go to the bottom because it tries to minimize the potential energy from gravity. So these are the points that the physical system will stabilize on. And this is the configurations that will give these symmetric and beautiful patterns that we observe. So we would like to kind of take advantage of this principle and apply it for the graphs, for the networks. So we can lead the graph in a state like the snowflakes or like the molecules that I showed before. So how do we do this? This is the point where we go from an abstract construction, theoretical construction, which is the graph with two sets, one of vertices and one of edges, and we make it into a physical system. So let's say we have this simple graph. We now consider the nodes to be spheres, or point particles, rather. And they carry charge, the same charge, actually, positive, all of them. So the equal charges repel each other. And whenever we have a connection between two of these point particles, we consider that there is a spring between them. So now we have moved from the situation of having this graph to a situation of having a physical system of charged particles connected by springs whenever there is a connection between them. And you can imagine that we can let this physical system evolve or try to find its minimum potential energy state and see what kind of layout we will get from that. Yeah, so that's the goal. But now doing this for the graph, having these physical properties, charges and springs between the nodes. In this case, though, the shape of the energy is not so simple. It's not just a one variable thing, but rather it's a complicated energy landscape, something like this, because there's many degrees of freedom. So it's the position of each of the nodes, and this has two coordinates for each node. So if we have v nodes, this has a dimensionality of 2 to the power of v. So even for 10 nodes, this has a dimensionality of 1,000, so roughly 2 to the 10. So it's a very large space to explore and try to find this minimum point. Just some comments about the forces that are acting between the nodes here, and this is the only equation that I will show. You might know that the electrical forces between charges depend on the distance between the charges, and they depend like the inverse of the square of the distance. And the attractive force between two ends of a spring depends linearly on the distance of the spring. That's the physical reality. That's the laws we know from Coulomb force and Hooke's law for electric charges and springs. But here we are free to modify them in order to have results that are maybe better. So in this case, for example, we can choose the exponent in the electric force, which is the repulsive, Fr, to be a general thing, P. P equals 2 in nature, but we can choose another value. We can choose 1 or something else. And also the attractive force, Fa, between the ends of the spring, to be proportional to the distance squared. Just because this kind of mixture gives better layouts. Also, and that's important, we can modify the dynamics of the physical system. So in nature, the masses would obey Newton's law, so a force would result in an acceleration, which has the effect actually of oscillations. So in a case like this here, when the ball starts rolling, it will reach the bottom, but it will not stop there. It will go to the other side and back again, and so on, in an ideal situation without friction. We would like our physical system to go to the state of low energy and stop there. So instead of using Newton's law, which says that the force results in an acceleration, therefore a difference in velocity, we modify that, and the force results in a change in position instead of a change in velocity. All I want to say is that we can engineer the forces and the dynamics. We're inspired by the physical system, but we can engineer it to be more appropriate for what we want to achieve. So let's look at an example about how this works. So this is a graph that we will use. All of you have seen it, maybe didn't think about it as a graph, but it is actually a graph, and these are the nodes on it. And it has 19 nodes, and the lines are the connections. So it has 39 of them. And we'll do what I said before. We will consider the nodes to be particles with mass, carrying the same charge, so they are being repelled, pushed away from each other. And the lines are springs, so whenever there is a connection, the nodes on the ends of the spring are held together. We will start with a random layout, just like I showed before, and see where this evolution of the physical system takes us. So here is the random positions. This is the same graph. You cannot recognize it, but it's the same graph with vertices placed in random positions. On the left side, there is some plots that I will explain later. But let's see what happens when we iteratively simulate the physical system that I described before with charges and springs, and see how it goes towards the configuration of minimum energy. So here there is some forces playing out. Whenever there is an edge, things are kept together, but all the vertices push each other away at the same time because of the same charge that they carry. You see that as time goes by, the system stabilizes, and you can almost see that it has some physicality due to this, in its motion, due to these physical properties that we gave it. And it gradually finds configuration of minimum energy. On the yellow plot on the left is the energy per node in the system, so you see that it is dropping, as we would expect. And the blue is the average movement of the graph with each iteration. So as time goes by, it moves less and less. Now, this is the same as the rocket. It doesn't look like the rocket anymore. To me, it looks more like this oceanic sunfish. But the topology of the graph is exactly the same, and it's actually a pretty good layout. Of course, the artist wanted to make a rocket, so he took the sides of this graph to be vertical. But this actually is a good layout, given that it distributes the nodes evenly in space. Let's see some more examples about how this technique works. So here is another graph that we don't know what it looks like. We just have information about the vertices and the edges, and we choose a random placement, and then let it evolve as a physical system. So you see again forces acting between the nodes. Connected ones stay close. Energy is dropping, and the system gradually stabilizes and kind of spreads or unfolds. As time goes by, it moves less and less. And here we have a more or less stable state. There's still some minor movement, but this will stop. And this is the graph that I showed before. That's what was our goal for that graph, and that's how we can reach it by doing this physical system simulation. Here's another example of a different graph. Again, one that we've seen before is the circular one. So you see the connected nodes stay connected because of the springs, stay close, and the electrical forces push everything away from everything else, and they are opening up the graph, giving us a circular layout. Okay. I have one more. These are all different types of graphs. Here's one that has neighborhoods, basically, very connected areas, that everything is connected to everything else inside, but only loosely connected to the rest of the areas of the graph. So you see there's all sorts of different structures that were impossible to see from without choosing a good layout. And this is something that we also cannot do manually, given that sometimes the graphs are very large. So this is an automated way to showing us, revealing us basically the structure of a network or of a graph. Okay, this is a good story, but what about the performance here? So if, let's say, we call n the total number of vertices in this graph, then for each of the nodes, we have to compute the n forces, basically, from all the other ones. And we have to do that for each of the nodes, so n times. So overall, we have a number of calculations that is roughly in the order of n squared. That's what this notation with the red means. And it's red because that's not a very good performance, meaning that it doesn't scale very well. So if, let's say, we multiply the size, we have a graph that is 10 times previous size, the number of calculations will be 100 times more because of this square. So there is a scaling that is very quickly going out of control and is impossible to handle computationally. It's, if, let's say, the graph gets 100 times bigger, the time we'll need will be 10,000 times bigger, and so on. We would prefer to have a more mild scaling, like this green curve, where we can increase the size of the graph, but not increase the time it takes so vastly. And luckily, there is ways to do that. And this can happen with basically not computing the force from all the other nodes that the graph has, but rather making an approximation for it. So we do this by partitioning the space in squares. And in this case, for example, we are looking at the bottom left, there is a yellow node. We're looking to calculate, let's say, the force on this particular node. What does this node see? So it sees each square in this picture as being one node. So the big squares that you see here, let's say at the top right, contain many nodes. But we are combining all of them in the center of gravity of this square, which is a blue dot. And we calculate only one force coming from that blue point. So this is equivalent, let's say, to when a car is far away, you see one light. As the car is approaching, then you start to see that there are actually two lights. Or if you see a city from very far away from space or from a plane, it looks like a dot. But only when you go close, you see the details and the different lights that make up this one light from far away. So what happens is, in this approximation, is that nodes that are far away from the yellow one, in this case, in the bottom left, are treated as one. And so instead of having to calculate forces from all the nodes, we only have to calculate as many forces as there are boxes here. So there is much fewer boxes than nodes in the graph. And this can give us a very good approximation of the total force and also the green scaling, which means it can be computationally tractable for big graphs. Okay, so that's good. We can be faster in our computation. We are not constrained by this bad and square scaling. So let's go to some bigger graphs. Now we have 200 nodes here, and let's see what's happening. So this is basically a big circular graph, bigger than before. Let's see what happens. As before, the physical system is trying to go to the configuration of absolute minimum potential energy, which is the circle. But we see that there is some nodes and twists that have happened there. And the system slowly is untangling those, but it is very slow at the end. And a lot of times it just stays in a configuration that is not the absolute or the total minimum, is a local minimum, as we say. So let's see it in another example that is even bigger. This is a graph with almost 1,000 nodes. We see that locally, the layout is good, so we can understand that there is some kind of surface there and some kind of grid structure. But globally, it's not so good. So there is these twists and folds that we would like to see untangled in order to understand the structure of this graph better. So why is this happening here? And why is it so slow to untwist those folds? The reason is that there is many nodes in these graphs, and in order to untwist them or unfold them, we're moving all of them, and for example, in a case like this, many nodes have to cross one side and go to the other in order for a twist to become level. So that's why it's so slow, and that's why we end up with some suboptimal layouts in this case. So what we would like, in order to be able to visualize even bigger graphs like this, is to be able to not only move the nodes, the graph, node by node, but to be able to move whole regions of the node, and then go into a deeper level of detail gradually, up until the point that we move one of these nodes individually. So I will describe a little bit schematically how this can be done. I will not go very deep into the detail, but let's look at the example that I showed before. This is, of course, a small graph. We already saw it laid out, but just to show how we can create, let's say, a rough version of the graph, lay out these rough features first, and then move progressively to more detail. So in this case, I don't want to deal with all the nodes, because there are many, and I have this problem of nodes and local minima that I mentioned before. So I will choose only some of these nodes. So let's say I choose the green one, and then I forget about all its neighbors. I forget about the white ones. Then I choose another one, the other green one, and I forget about its neighbors. Somehow, I don't forget about them, I just put them all together with the green. So all the white ones are represented by some green node. I don't have to deal with them at this stage. And I continue this process. So I choose another green, and I combine it with the white that are connected to it. And so on, until I complete all the nodes of the graph. And so now remember, I only look at the green ones, so I have a structure that looks like this for the more complex graph that I showed before. So I will do the layout in this. We can do the layout in this graph, which is simpler and will not have all these nodes and folds. And then we can add further level of detail by adding the neighbors that we removed and so on. And this actually can be done recursively. So I can even simplify this graph into just 2 nodes if I want it. Of course, this is already a skeleton of the original graph. But in very, very big graphs, we can do this process many times. So the idea, again, is that we are laying out the rough parts of the graph. Then we go inside the rough parts. We lay them out separately. And that continues until we are finished with the graph. Just as some visualizations of what we can do using this technique, here is how the previous example that I showed that was full of twists and so on looks like when we do this modular or multi-level laying out. And we can even do bigger ones like this with more than 4,000 more nodes and more than 12,000 edges, and see some interesting structure. inside, or like this, or like this, or like this. And we can basically achieve good layouts efficiently for very large graphs that are quite often encountered in many scientific problems, and understand the structure and the connections between all these pieces that are inside. And with this, I would like to thank you and answer any questions you might have.
Hi.
Hi.
Have you thought of modeling directed graphs, like when you have information flow from one person to another?
I have not done this. So in this case, perhaps you could imagine that the force is going from one, but not from one node to the other, but not back. Which this is also a quite radical modification of the physical law, but it would be worth trying. But I have not done it.
Thanks for your talk. Did you try to look at the features of such beautiful graphs? I mean, making some min cut or subtrees and subgraphs, some features of the graphs which can show that that graph will be beautiful and that one will be ugly.
Oh, you mean before the layout, before the visualization?
Before the visualization, yeah.
Yeah, one kind of processing that we have done is clustering sometimes before. So that can give you an idea of some kind of structure if it exists, and also can help you with the layout because it will give good initial positions, let's say, to the nodes. But that's what
Thanks.
I've done, yeah.
Yeah, thanks for your talk. I recently did some simulations on nonlinear oscillatory networks. So I have the nodes are oscillators and they have a random initial frequency. And when I evolve the system, they tend to, several nodes tend to synchronize. So they take on the frequency of their neighbors. And in the end, I have clustering. So I have a lot of nodes that preach the same frequency until I have maybe a cluster when every node is oscillating on the same frequency. It's based on the work of Professor Kuramoto. I'm not sure if you have heard of him. Did you use your kind? Do you think it's possible to use your techniques on this kind of simulations? Have you ever heard of this?
I'm not familiar with his work that you are mentioning. To me, just hearing about it now seems like a resonance situation that you have with different frequencies that coupled,
coupled
oscillators in this in the system. I can see connections between there is, coupled oscillators here with the springs as well. Even though, as I said, the forces and the dynamics are modified in this case. But yeah, it would be interesting to explore the connections. Right now, I don't know if in your case, the same treatment applies because here we're dealing with forces. I think maybe in your case it's a more algebraic problem of the coupling matrices in the
Yes, exactly.
in the graph.
Yeah.
But maybe there is some analogies.
Are there any other questions from the internet? Okay, so I close the talk. Thank you very much, and big applause, please.
Thank you.